Hello students, this is the second lecture on diffraction phenomenon. The first lecture is given in the last session. Before going into this lecture, I would suggest my student to see the last lecture, and the link is given in the description box. So a little recapitulation of the last lecture. In the last lecture, we have seen that the interference is the superposition of two waves or few waves, and diffraction occurs due to the superposition of many waves. And we used the Huygens principle to handle the diffraction phenomenon. Huygens principle says about the propagation of wave through an arbitrary medium. This principle says that each point on the wavefront at time t equal to 0 acts as a source of secondary wavelet, and after a later time the wavefront is the envelope of all such wavelets. So the plane waves remain plane wave after a time, and also the spherical or cylindrical, whatever may be, it remains the same. In vacuum, it is quite applicable, but if you wish to find the propagation of wave through an isotropic medium, then it becomes quite difficult, because in an anisotropic medium, the speed of light is different in different directions. And according to the Huygens principle, every point on the wavefront acts as a source of secondary wavelets. And if we wish to calculate the intensity produced by the aperture at a distant point on a screen, we have to consider the superposition of the secondary wavelets emitted by all the secondary sources. That is, to find the intensity distribution on the screen, we need to consider the contribution of all the point sources at the aperture and the superposition of all the wavelets coming from all the secondary sources. This is a narrow single slit diffraction pattern, and this is a narrow slit. This is a slit on an opaque plane, and plane incident waves are incident on the slit. The width of the slit, this is y-axis, and the width of the slit along y-axis is b. And let us take the section along this direction. So the section of the slit B along y direction looks like this. This is the section of the slit along y direction, and that depth is b. So, and we have considered ignored all other dimensions in comparison with the dimension b. Why we have neglected the other dimension, the larger dimensions, that will be cleared in the next few slides. Okay. If we consider at some point which is at an angle theta, this angle is theta, away, the secondary waves are going to contribute through a phase difference. That phase difference is due to the path difference. Here, if we consider these two waves, then if we draw it perpendicular on the line, then this distance is the path difference between two consecutive waves, and that path difference is equal to y into sine theta. And the secondary waves are going to contribute through a phase difference. That phase difference is equal to two pi by lambda into pi into the path difference, that is y sine theta, and we can write 2 pi sine theta by lambda is as equal to k, so delta is equal to k into y. Thus, if the source or the secondary source is shifted from the origin, there exists a phase difference delta, and if we take into consideration all these sources to contribute at any point on the screen, then we need to add up all these, and for that we need to integrate from minus b by 2 to plus b by 2, because in the last if we take it is as an origin, then the slit width varies from minus b by 2 to plus b by 2, and at the origin we are considering an element of length dy. Here we have considered an element dy, and after a distance y, the after distance y, the amplitude of the secondary waves that come from the element dy, we can be written as d e tilde equal to e naught tilde dy. So integrating from to get the contribution from all the sources, secondary sources, we need to integrate from minus b by 2 to plus b by 2, and this gives e tilde equal to e naught integration minus b by 2 to plus b by 2 to the power I k y dy, and integrating it gives e naught to the power I k b by 2 minus e to the power minus I k b by 2 by I k, and this gives e naught from these these terms we have 2y sine kb by 2 divided by I k, and this gives e naught b sine 2 b pi sine theta by lambda divided by b pi sine theta by lambda, putting the value of k in the equation. So we can write e naught b sine beta by beta, where beta is equal to b pi sine theta by lambda, and the intensity from the resulting intensity from an idealized coherent source can be written as I theta is equal to half e tilde square. This is a complex conjugate of e. So from this we can write it is equal to I naught sine beta by beta square is equal to I naught sin square beta. Now when if we plot sin square beta in this direction, we have plotted I theta by I naught and here beta. So the graph shows, sin square beta graph shows like this. This is the intensity distribution. When we have the expressions I function of theta is equal to I naught sin square beta. So when theta is equal to 0, sine beta by beta is equal to 1, and I theta is given by I naught. When theta equal to 0, beta is equal to 0. So sin beta by beta equal to gives 1, and sin theta, I theta is equal to I naught, that corresponds to principal maxima as theta this is not a full stop, as theta equal to 0 here. Theta equal to 0, so it gives the principal maxima. Let us consider if we consider the geometrical consideration of light traveling. Then if the light travels in this direction and in presence of the lens, the light would traveling through the lens, it would get focused at the center, at the focal plane here. So we considering the geometrical optics, we should get a bright patch at the center. No finite width. Only a bright patch should be observed. But considering the Huygens Fresnel diffraction pattern, we get a sin square function that is with a central maxima of a finite width, and then we get maximas but much less intensity, but the central maxima is very bright but with a finite width. Okay. Thus, the intensity resulting from an idealist coherent line source in a Fraunhofer approximation is I theta is equal to I naught sin square beta, and sin square beta function gives the intensity distribution like this. When B is very much greater than lambda, B is the width of the slit. B is very much greater than lambda, the intensity drops very rapidly as theta deviates from 0. Okay. And when lambda is very much greater than B, beta is small, and sin beta equal to beta gives the I theta equal to I naught, that is a constant spherical wave. We get constant spherical waves. If theta is very much less than 1, then I theta is equal to I naught sig square pi b theta by lambda. Theta equal to 0 gives I theta equal to I naught, gives the maximum value. This is the maximum value that we get here. Now, what should be the spread? I have said that it has a finite width. So, what should be the width of the central maxima? So, the width, we get this width of the central maxima. We can get this width of the central maxima by calculating the position of the minima. If we calculate the position of the first minima on both sides of the central maxima, then we get the width of the width of the central maxima. So, to get the minima, beta equal to plus minus m pi will give the beta equal to plus minus m pi is give the value 0. So, in that case, I theta is equal to 0. And for m, and m varies from 1, 2, 3 and so on, as because m equal to 0 gives the position of the central maxima. So, for m equal to 1, we have beta equal to pi. So, the value of theta, beta equal to pi b theta by lambda. So, putting this, we get theta equal to, for beta equal to plus minus m pi, theta is equal to plus minus m lambda by b. So, the position of the first, to get the position of the first minima, we should write m equal to 1. So, theta is equal to plus minus lambda by b. So, this position is minus lambda by p and this position is plus lambda by b. So, the width of the maxima is 2 lambda by b. The spread of direction, what is called as, the spread of the direction is called as the diffraction. First minima occurs at lambda by b. So, the comparison of the slit with the wavelength gives the idea of spread of light. So, b, so the width of the light, width of the central maxima is 2 lambda by b. So, as b small, if b is small, then the width is larger, because this width is 2 lambda by b. If b is smaller, then width will be larger, and if b is larger, then the width will be smaller. So, the dimension b gives the diffraction pattern, and we can say that the smaller the value of b, the larger be the width of the minima. The larger be the width of the maxima. So, we can say that we can neglect the other dimension of the slit in comparison to the slit width in which direction the width is smaller. So, that's why we have taken the let's move to previous slides. So much time. Okay, that's why we have taken the intersection along this direction, and we have neglected the other large dimensions, because the smaller is the width, the larger is the diffraction, and the larger is the spread of light, and the spread of light is termed as the spread of light is termed as the diffraction. So, that we get the intensity pattern like this. Okay, smaller the value of b, larger be the width of the central maxima. That's why we have taken the smaller width dimension. Now, if in practice the slits are not one dimensional, in reality they are two dimensional, and in that case I theta can be written as I naught sin square beta x sin square beta y, where beta x is equal to b pi bx sin theta x by lambda and beta y equal to pi by sin theta y by lambda, where bx and by are the dimension along the x direction and dimension along the y direction, and correspondingly theta x and theta y along the x direction and y direction. So this is the rectilinear propagation of light, but due to the presence of the aperture, small aperture of small width, the lights get refracted along other direction. So now we have to calculate the position of maxima and minima. We have I theta equal to I naught sin beta by beta is equal to I naught sin pi b theta by lambda. Actually we have sin theta here, and for small theta we have considered sin theta as theta. So I theta is equal to, can be written, I as a function of theta can be written as I naught sin pi b theta by lambda divided by pi b theta by lambda. And for pi b theta by lambda is equal to m pi, it should be m pi, is equal to m pi plus minus m pi. This gives the value of m plus minus m lambda by b. Remind you, this should be plus minus m pi, which gives the value of theta equal to plus minus m lambda by b. So the first minimum occurs at theta equal to plus minus lambda by b. And in order to get the maxima, position of the maxima, let's differentiate I as a function of theta with respect to beta and equating it to 0. That will give the position of maxima. So differentiating, we get I naught 2 sin beta cos beta by beta square minus 2 sin cube beta by beta cube equal to 0, and this gives sin beta into beta minus tan beta equal to 0. Sin beta is equal to 0 or beta equal to m plus minus m pi corresponds to, so sin beta, either sin beta equal to 0 or beta minus tan beta is equal to 0. So sin beta is equal to 0 gives the position of beta equal to plus minus m pi, which corresponds to the minima. So we have seen earlier. So the condition for maxima are the roots of the equation beta minus tan beta equal to 0. The root beta equal to 0 corresponds to the central maximum. Then the other roots can be found by determining the points of intersection of the curves y equal to beta and y equal to tan beta, and the intersections occurs, these are the tan beta curves. These yellow curves are the tan beta curves, and this is the beta curve. This is y equal to beta, and the green curve is y equal to beta, and the yellow curves for the tan beta. So the intersection occurs at the points beta equal to plus minus 1.43 pi, plus minus 2.46 pi, plus minus 3.47 pi. And the intensity of the first minimum, let us write it as I1 equal to I naught equal to sine 1.43 pi by 1.435 for the value of beta. We have written here 1.43 pi divided by 1.43 pi whole square, that gives 0.0496 I naught. Thus the intensity of the first maximum is about 4.96 of the central maximum. So the intensity, this is the central intensity, okay, and the first maximum is has the intensity 4% of the central maximum. And the second maximum has intensity 1.68%, third has 8.3%. So you can see here that the intensity goes on decreasing. So the first central maxima has a larger intensity, and the position of minima, according to the graph is according to our calculation, the position of minimas are pi, this is position of minima, pi minus pi, then 2 pi, minus 2 pi, then 3 pi, minus 3 pi, and so on. And the position of the maxima, this is the first maxima, the position of the first maxima is 1.43 pi, second maxima is 2.46 pi, and accordingly third is 3.47 pi, and so on. So this gives the intensity distribution of the diffraction phenomenon. Okay, thank you for watching.